It's my disadvantage that I'm speaking after lunch. Anyway, so basically it's not a talk, okay? I'm not here to give a lecture. So don't call it a lecture. So we will try to share experiences. So whatever I have seen, whatever we have done, those I'm going to share with you, and we'll interact throughout this particular session. Okay? And please interrupt me anytime you like. There is nothing serious about this. Like we have been doing this, we have been watching PPTs the entire life, right? So we will try to keep it very simple. We'll try to make it as interactive as possible. And I believe that you cannot learn everything from this session of 2 or 2.5 hours. It is not possible for a human being to get everything in this short period of time. So therefore, we'll just talk about philosophies. We'll focus on philosophies of simulation and modeling rather than on the results and the ways in which we have done. So which may help you to get these ideas and apply this in the same context, somewhere where these areas align or intersect, right? So that should be the motivation, or that should be the objective of this particular session. So I've been given the topic modeling and simulation of emerging electronic devices, which is a very vast area, right? And you can even call about modeling, starting from modeling a very simple semiconductor device, modeling a lattice, and up to you can go from a lattice to an entire exclusive device like a field effect transistor or a memristor or similar devices, right? So therefore, speaking about the vastness of the topic, I have kept certain restrictions, which we now call as like constraints whenever we are doing modeling, and those will be focusing on a few devices: tunnel field effect transistor and thin field effect transistor, and then within those we are going to look into the different case studies. So I have designed my entire slides into different case studies, right? So there we will be able to see like what philosophies we do. So thank you for the introduction. And yeah, so this is the group where I work, Technology and Semiconductor Device Lab, and we do work on simulation modeling. We also do some on and off works on fabrication also. And apart from that, we also have an exclusive interest for education, technology enabled learning. Okay, so there also we work. So yeah, before moving into the actual lecture, let's try to connect these pictures. Yeah, anyone? Can we get something from this? Okay, so this happens to be 8th January, which is Earth Rotation Day, Stephen Hawking, which is birthday, and the death anniversary of Galileo. So before starting, we need to respect those individuals who have contributed to science and technology throughout. And so it is our duty to remember them whenever we like encounter these occasions, because these are the only occasions when we can remember them. So this is the design of the contents, okay, and we will start with field effect devices, Moore's law, contemporary technologies, and basics of modeling and simulation. I feel that rather than the second part of this lecture, which is also very important, these parts are very important because that is where we get stuck before doing an actual kind of a simulation or a modeling. Okay, so that is where our philosophies should be correct before moving into the actual work. So therefore, I feel that this part is important, although it is a very little part. We are not going to have many slides, but we'll discuss more on this before moving into the actual case studies. So basic ideas. First of all, the field effect in devices, and Julius E. Lilienfeld, most of you must be knowing. So he had already filed a patent in 1928 for field effect, and later on in 1947 and 48, when Shockley, Barton, and Brettake they went for the point contact transistor, they also had the field effect clause in their patent claims, right? But that was rejected. Most of them were rejected because Lilienfeld had already filed this patent for device for controlling electric current. So this is one of the instances in history, and this happens to be the diagram which Lilienfeld filed in his patent. And after that, we already know about MOSFETs. So who invented MOSFETs? So basically there were many groups who were working at that time, and it is also sometimes called as the conspiracy of the, you can say, semiconductor industry, because there were many competitions going on at that time to reveal or to develop devices which can outperform the junction transistors. So therefore Atala and Kang and Bell Labs, they, while working, they built the insulated gate field effect transistor, but their work never got a wide recognition because it remained in the papers. There were these, you can say, corporate laws and everything. So therefore, I mean, in 1962, Hackman and Hofstein, they built the ITFET, and it is also considered to be one of the most important or relevant as related to the invention of MOSFETs. So this is some basic idea, and the Moore's law. So Moore's law, we know that there's a doubling of components, right? On a specific die area, the number of components double because that is the as per the demand. Okay. Now the problem with Moore's law is that we only look at it from the perspective of doubling of components. Okay. We only know that Moore's law states that within every 18 months or 24 months, the number of components double, right? But what is the actual, you can say, motivation behind this doubling? What is the actual motivation that you can find behind this doubling of components? So if you observe, if do you know how this law came into existence? Moore, this was not a law, okay? This was not a law before. Moore, he observed only 3 data points from the fabrication units of, I think, 3 or 2 industries at that time, Fairchild and probably one of them, I forgot the name. Just by observing the 3 points, he said that probably in the next 2 years or 4 years, this is going to happen. So he just drew a sketch, a graph kind of a thing. So basically, it's not a derivable law; it is an observable law. Okay, it was like you observe a pattern and then you say that this is going to happen. Now the industry felt that since the demand of the industry, the demand of the customers, which is us, or the companies which wanted electronics during that time, they also had this particular demand where this exponential growth was important. So therefore this became a law. The industry adopted this because they felt that if they could double the number of components in this particular set of months, then this is going to sustain the demand of the industry. So then it became a law, right? So basically, if you observe, the connect is not something like I said. He said one day and just wrote something. It was not that. He was actually relating the number of components to the demand of the industry. So therefore, the Moore's law is basically related to the economics of the semiconductor industry. Okay. So rather than just stating that it is just doubling of components, so it is basically related to economics, and this is what appeared in the Economist in 2015 related to the Moore's law, where it clearly stated how the Moore's law is related to the economics of fabrication and all the stuff. Okay, so therefore Moore's law is not simply a law; it is the basis or the heartbeat of the semiconductor industry, which is actually propelled by the economics of the industry and not simply the number of components. Okay. So these are just basic, you can say, parts of understanding transfer characteristics. So I'll not go into this. Yeah. So this is one video from Intel. I think can we play that? Will we have sound? Okay, so recently, I think in 2021, Intel and Samsung, they both went for the gate-all-around structures of devices, which is basically which this person is going to speak. And when we talk about MOSFETs, these are planar structures, right? The gate is just over the channel, and it stays there. But in case of FinFETs, you automatically you may convert it into a 3D fin kind of a structure where you have gate to wrap around that entire structure. So you have control from all three sides of your channel. Okay. So therefore, FinFET is like very similar to your MOSFET, but MOSFET is planar, therefore you do not have much control over your carriers in your channel. So therefore, when you go for a FinFET, then you have gates wrapped around from all sides, all three sides or two sides depending on the design, and so you can have that particular better control over electrostatic control over your channel, as a result of which your short channel effects are going to decrease. So if you have any doubts on this, I can do some talking on the board. Our components research team has been working on this for many years now. In 2019, in early 2021, when I was driven, the next is stacked on top of each other instead of side by side in order to make smaller footprints, freeing up space for more resistors. Stacking resistors like this allows to reduce the footprint of logic devices 30 to 50%. Our component team has been working on this for many years now. In 2019, we presented a paper that showed industry's first ever silicon CMOS laser resistor on top of gallium nitride CMOS. We made the different layers in a sequential order via 3D layer tracer technique. At the same event, we also showed a record performance CMOS device on top of a silicon NMOS filter. Again, this was built sequentially via 3D layer tracer. Now is for both heterogeneous stamps, meaning we mixed a silicon resistor made out of the resistor from another type of semiconductor material. In 2020, we presented first silicon on silicon ribbon cut NMOS on ribbon cut CMOS device, built using a self-aligned process. What does self-aligned mean? It means we can build both layers in one step, rather than building them separately and bonding them together. This helps with alignment issues and reduces manufacturing steps. At this year's IEDM, we compared two approaches, the self-aligned one and the sequential approach. Spoiler alert, we prefer the self-aligned one. These are just a few examples of future transistor designs and structures that we are researching here at Intel. There are many more to come. Okay, so before moving into simulation and modeling, just let me say what this video was all about. Okay, now if you have a MOSFET and if you look at it in a 3D structure, okay, so you will be having its source and you will be having its drain, and on top of that you will be having your gate structure. Okay, if you see it in its 2D form, it is something like this, right? will look something like this. Okay, where this is the gate, source, drain, and your body. Now, the problem with this is that when you are shrinking your device dimensions, your short channel effects start to appear in this device because your gate, which is your third electrode, has now lesser control, and your source and drain are overpowering and they have the control over the channel. So basically, it is the termination of electric field which comes from the carriers in the drain over the carriers which were supposed to be controlled by the gate. So now the gate has lesser control over your channel, and you do not want that, and that is basically the origin of this short channel effect, the charge setting, right? Now what they did, basically Chemin Hu was given a project and he thought that if he could somehow increase the electrostatic control of the gate over the channel without modifying the principle of operation of the device, then it would be a huge boost to the existing industry, because you cannot start changing the fabrication lines every time, right? Because you have invested, the industry has invested, so you have to think about a solution which can be consistent with the technology which you have, right? So therefore FinFETs, their principle of operation is similar to that of MOSFETs. The only difference is that they have a kind of a feed structure, where here your body is simply like a straightforward kind of a thing, and you have just a planar structure on top of this entire, you can say, channel. But in case of FinFET, the gate will wrap around the entire device. So the gate oxide and your gate will have control from all the three sides, or sometimes it is also based on two sides depending on the thickness of this. But basically you are going to increase your electrostatic control over your channel. So that is the basic concept of FinFET. Now once you do this, what you are doing is, although your drain is trying to capture more kind of you can say carriers from your inversion layer, but still your gate, you have increased your control of the gate over the channel by wrapping it from all the three sides. Okay, it is just like attacking a particular army, right? If you attack from one side, the effort will be less. If you are attacking from all the sides, your control will be more. So the same analogy can be developed here. So here in this video, what they are talking about, that they are already done with the FinFET technology. They have scaled down the entire FinFET technology, and now they want even better performance, right? Because once you are scaling down your devices, ultimately you are going to reach a point beyond which you will have to think of another technology. So that is where these ribbon-fed architectures come into existence. And what are these ribbon-fed architectures? They are going to stack these pins on top of one another. So basically it is going to look something like this. So here is one pin which will come out. Here will be a second pin which is going to come out, right? And this is your entire gate. So this is a, you can say, the front view, right? So using a single structure and vertically stacking your devices, you can have better control and you can have more drive current. So that is the concept of, you can say, ribbon FETs which Intel introduced. And similarly, Samsung also went forward and they announced similar kind of a technology, but since they cannot name it ribbon FET, so they have named it gate all around nanosheet FETs. Okay, so these two are similar technologies in which Intel is working, and along with that, even Samsung is working. Samsung calls it gate all around nanosheet FET, and Intel calls it the ribbon FET. Okay, so this is basically they are talking about this. Now they are also talking about heterogeneous integration. They have compared two architectures, one in which silicon device was put on top of gallium nitride device, and another in which they had only this pin ribbon kind of structures. And they found that this ribbon kind of structures gave better performance as compared to heterogeneous integration of planar devices. Okay, so that is the basic idea of this device, of this video. Sorry. Now, as the topic goes, simulation and modeling. Okay, now this already has many confusions, and this also has many myths when we are talking about simulation and modeling. For some researchers, simulation is just taking a computer and designing some results. Okay, you give an input, the system is obviously going to give you an output because it is a computational device, right? And modeling is mathematics, right? So that is how we perceive simulation and modeling. Now, people who are doing fabrication and who love doing fabrication, so they will give more emphasis on fabricating a device because that is where we see the real characteristics, right? and that is true, you cannot deny that. But at the same time, simulation and modeling have been growing as like consistent and you can say inseparable parts of device performance. And the reason is that we are, on one hand we are having an increase in the computational efficiency, right? And on the other hand, this simulation and modeling help us understand devices better, develop models better, and as a result of which you can also have circuit realizations better, because in circuits before you tape out, you'll have to understand how this particular device is going to work in a circuit, because the devices which we are making or which we analyze, that has no importance at all until and unless it is going into some kind of application, right? During an entire lifetime, a person he designs devices, but if that device does not find the market or it does not find the opportunities for which it is designed for, then I think that has reduced value as compared to something which you have already transformed into the circuit or an application kind of a perspective. Okay, so now therefore with that relation we'll go into this simulation and modeling and what should be the basic approach. So it is never like earlier there was a misconception that on one hand this person has done simulation, this person has done modeling, right? So it was like simulation versus modeling, okay? But that is never the case and it cannot be in any kind of scenario. So first of all, why is a device model important? So what do you understand by a device model? What is a device model? If we talk about device model, so what do we get from these? So basically, if we are talking about a device model, so let me say that I have a device where the current linearly depends on the voltage. So basically, it is like I equal to M into V plus C, something like that. Okay. Now, basically, this is going to describe my actual device, which I am going to fabricate or which I have already fabricated. Okay. Just try to understand the link between the two. Now, the accuracy of your model will depend on how close you have tried to mimic your actual device or the device which you have fabricated or you are going to fabricate, right? Once that comes into picture and you know that nature is never going to give you straightforward answers, you cannot exactly define something with some kind of an equation, only a single equation, because there are many dependencies, there are many parameters in nature, right? So therefore, now it depends on you as a designer how you are going to develop that. Okay. What you are going to see, first of all, if you are taking up a device, first of all, you'll have to set your constraints. You cannot design an equation which is valid for all kinds of, you can say, parameters. If it is the most ideal kind of a model, right? But there will be some conditions, there will be some criteria in which this particular device, your model is going to work or describe the device better. So first of all, as a designer, you'll have to identify those constraints. Like you are going to do this model for what kind of applications or what kind of conditions of the device. So that is the first part. And device models are important because whenever you are going to perform or whenever you are going to apply these models to some applications, you need a background equation, right? So if you can form a closed form equation, then that is going to help you realize the circuit application of this device. If we are doing devices, if we are doing semiconductor devices or field effect devices, basically we are doing for some applications, be it circuit, sensing or some other kinds. Okay. The ultimate goal is dropping it somewhere where it is getting applied in some kind of areas. Clear? Now, therefore, device models are important not just to write an equation and plot a graph. Device models are important because those are going to, you can say, mimic your actual device, and it depends on you how accurately you have defined it. Then why is device simulation necessary? Now see, suppose I have developed my model, okay, I equal to M into V plus C, okay. Now, if you ask me at a voltage of 3 volts, what will be my current, right? So earlier I would have calculated, but now I will use a computing system and then I'll tell you, okay, these are the things, okay. Now just try to look at it at an advanced level, okay. Now you have a device which is complex in nature. Take for example a MOSFET or a field effect transistor, where you can give your drain current based on the equation which you have, right? But if it is a different device, an advanced kind of a device, then you'll have to design it and you will have interdependent functions. So one function is going to depend on another, this is going to depend on another. So the accuracy will depend on the accuracy of your computing system. Okay, this is where computing systems play a very important role whenever we are talking about actual implementation of device models. Right? Now the problem with this is that device model was equation, your computing system is also running an equation, isn't it? So don't you think that both are equivalent? So just try to understand the philosophy. I have a computing system, I have a very good industrial simulator, okay, there installed. So I do not have to worry about whether it is accurate or not. On one hand, I have also developed my own system, my own simulator based on some equations which I have developed. So aren't I and that computing system doing the same task? Isn't it? This is also running some kind of equations. I am also running some kind of equations in my system. So both are actually logically equivalent. So therefore, device model and simulations can be said to be logically equivalent to one another. Okay. So that is the reason why it is never modeling versus simulation. It is always modeling and simulation, because simulation is dependent on different models. The models are basically your mathematical functions, analytical functions which describe a device. Okay. Now let us try to take an example here. Then maybe it will be clearer, like the equation which I was running and the equation which this industrial simulator is running, which is more preferable. Right? Now, for example, you can buy some foods from the market, and the same food also you can prepare at home, right? But there will be a difference in your taste. The food you purchase from the market will be better in most of the sense in terms of taste. I'm not talking in terms of nutrition, okay? And the one prepared at home may be a little bit less tasty, okay? My point is that the one brought from the market that has been designed exclusively for the taste of the customers, so that every experiment or every test that it has passed through, it is basically targeting the taste of the customer, you can say, values, right? So now, if you are going by the taste, then you are going to obviously buy this. If someone comes into your home, you are going to buy that product because you already know that is already tested. Same goes with industrial simulators. So once an industrial simulator is launched, remember that there are many years of, you can say, experiments and tests which have been done, and there are also default models which have been verified for existing devices, right? So that is the industrial simulator which this computing system was doing. Now come to my one which I have developed. So basically what I will do, I will take a device. Then I will identify the constraints. Okay, I will be doing my simulation, I will be designing my model only for this constraints. Temperature range will be 300 to 350. Then it cannot give the current if there are, you can say, traps in the device or defects in the device. So there will be many constraints in my entire, you can say, model. Okay. Now you tell me, if I go in the market with my model and if I take the industrial simulator with me where you have varied options, then you are obviously going to buy the industrial simulator. You are not going to buy my model, right? So therefore we need to understand why industrial simulation is very, very important. I am not saying that the models which you develop are useless. Okay, they are also important, but people will prefer a product which has wide range of, you can say, applications rather than a product which will only give you something related to a single device. Okay, so the point is that it is never something like your model is worse than the model which is done by the computer, but this has more trust value. Yours is just new in the market. Yours has limited constraints. This has more number of options. This can also do traps. This can also do drain-induced barrier loading concepts. Your model cannot do that. So basically that is the difference, and that is where people mistake between device modeling and simulation. But actually both are logically equivalent. Is this clear? Am I able to reach out to you? Okay. So that is the philosophy, and we have to understand this. So whenever you encounter statements like Simulation is nothing but you sit in front of a system and then you put some data and you're going to get an output, right? So that is not actually true, because with simulation there also comes some responsibilities as a designer. Those we are going to see, the ethics of doing simulation and the ethics of doing modeling. Basically in modeling you don't have much ethics to look out for, because it is the truth that you are going to see. Mathematics will always give you truth, but in simulation there are ethics which you need to follow, or I would like to say on a less stricter sense, that you have to follow some guidelines which will keep your research at a particular standard. Okay. So one of them is calibration. Okay. Now, when we talk about calibration, so there is only one meaning which comes out to us, that we are standardizing our setup with something which is already standardized. Okay. In simulation also, calibration is very, very, very important, right? In earlier days, this was not an important, you can say, calibration was not an important component of research, because in those days you had bigger devices and models which were developed at that time in classical forms. Those were almost considered to be applicable to all those devices. Okay, applications were few, there were fewer, you can say, explorations in devices. But now, and especially with the advent of the, you can say, after the Moore's law and after the processors came into existence, so this thing became very, very important. Okay, now for example, I am an industry and I am approaching you. I know that you are doing simulations on a very modern device which has recently been discovered. Okay, and you are doing some modifications in that device, right? And I have already developed that device. It is with me. I have already fabricated that, and you are doing a modification of the architecture of that device in simulation platform. Okay, is this clear? Is the condition clear? Okay. Now you are saying to me, I am the industry which developed this device. You are telling me that come and buy my, you can say, performance parameters. I have developed this by modifying your device, which is my device, which I already have. You have designed and predicted performance of a modified version of my device. Okay, so that is the condition. Now tell me, based on what trust I am going to buy your parameters? Because I am buying your parameters so that I can use those parameters to design the modified version at a reduced cost. That is my main motive, right? So it means that if you are telling me to buy your performance parameters or your simulation framework, it means that first I will ask you, have you calibrated your simulation? Okay, that is the first question I'm going to ask you. How am I going to trust your simulation? Because simulation means there are already equations. You have just put the device and it's going to give you your output. So my first question will be, how am I going to trust you? Do you have calibration of that particular device? Then there the major problem starts. Because remember, doing research is a different thing, and doing research to satisfy the industry demands, that is a different thing. Okay, if I am an industry, I am going to look at your research in a very different way. I'll be only looking at whether your research can give me money or not. Okay, and that is logical, right? That is nothing wrong in that, because I have developed this device by investing my amount. It is already working. Now suddenly you come up and claim that I have modified your device. You tell me that you have modified my device and you want to sell it to me, right? So obviously I will be demanding, I will be trying to look whether your things are okay or not. And how am I going to do that? By looking at the first step. There are many other steps, but the first step is calibration, whether you have done calibration in your simulation. So how do you do calibration? Now we are going a step backward, and now we are in the research domain, not in the industry domain. Okay, because to understand the essence of calibration, you'll have to understand the philosophy of calibration. So basically, suppose this is a new device which I have developed. Okay, and I am going to simulate this. I have designed this device on pen and paper. Suppose I have designed this and I think that this is going to work. I perceive that this is going to give me good drain current, and I also think that this may replace MOSFETs. Okay, so that is the hypothesis, right? Now, it means that I will be designing this device in an industrial simulator or any kind of standard standard simulator, and I'm going to predict its results. Okay, clear? So first of all, I have to calibrate this. Now, how am I going to calibrate this? Basically, as I have said a few minutes back, a simulation framework, no matter how advanced it is running. There are various models and mathematics running behind them. Okay. So to understand a simulator, first of all, you'll have to understand what device models or what models it can use. Okay. Clear? So, for example, if you have drift diffusion model, you have to know what the parameters of the drift diffusion model are. If there is a tunneling model, you'll have to understand whether it is local tunneling or non-local tunneling. Okay. So basically, you'll have to know the simulator first before simply sitting and just doing your simulation. Okay. So that is the first one. So you have different models, and basically these models, most of them are derived, and there are many empirical terms in them. There are many fitting constants, there are many parameters which are available for change from your end. Okay. So if it is, for example, as I have said, if it is I equal to mv plus c, then you cannot alter v because that is a voltage you are going to apply. You cannot change I because that is the dependent variable, right? But m and c is in your hands, and you can see whether by altering them you can mimic your current voltage characteristics with the actual device. So basically, this is a very simple example. In simulation framework, basically in any kind of industrial simulators, you will have different models which are basically mathematical functions. And if you know those mathematical functions, you will see that there will be certain parameters. You'll have to identify those, and then you can change them and bring your device characteristics matched with a fabricated one. So that is the essence of calibration, and that is how we start with calibration. Okay. This, now remember, whatever I am talking now is before doing any kind of simulation on my device. I have not yet started simulation on my device. I am only setting up my design. Okay. And finally, we'll be seeing which parameters we have to look. So basically, in most of the cases, it is current versus voltage. Okay. Either it will be transport characteristics or it will be output characteristics. So Y will be current and X will be voltage. And based on an existing experimental data, I will try to mimic my simulation with those data which I have got from the experimental device. Okay. Now, there is you can say an exception here. In some cases, this Y and X may not be always current and voltage. Okay. For example, if you are designing your device and you want to check in terms of mobility, and you want to calibrate the mobility, then Y will be mobility and X may be some dependent variable. Okay. So therefore, I have not generalized it as voltage and current. But the only, you can say, fundamental point is that before doing the actual simulation, you have to calibrate your setup. There is no way you can move into the actual simulation without doing a calibration if you want a standard, you can say, research outcome. Clear? So selection strategies, like for example, as I have said here, this is one device which I have designed, which I thought from my mind, which I thought that this is going to work, but I am yet to check its, you can say, characteristics. I only thought about that, right? But in order to see which device I am going to calibrate my setup, because this is not fabricated yet, you cannot calibrate your setup with this device because you are going to check this device. So you will have to calibrate with something which is already available. Okay. Now, if this design is very, very new, then how are you going to decide which experimental device you have to select? Are you getting my point? Yes. I have a new product and I don't know with what to compare. So you have to first know with what you are going to compare, right? Then only you can say, okay, this rating is 4.5, this is 4.2. If I do not have anything, this is the first time I am doing. So then it becomes a challenge, and that is where acceptance of articles also become very difficult, because people are not going to believe in you that you have developed something so new, right? So therefore, that is another point where and why calibration of your setup is very, very important. You'll have to make the scientific community believe that you have actually calibrated and you have actually taken instance from something which is available in literature. Okay. So this is the other perspective of doing calibration. Okay. Now here, so first of all, the question that you need to ask is, does your literature have a fabricated device whose principle of operation it has some kind of similarity with the device which you are thinking about? Are you getting my point? I have developed a device which works on, say, quantum tunneling. Okay, I think that it works on quantum tunneling because I have arranged my junctions in that particular format. I have placed my gate in that particular format, and I'm expecting it to behave to have some kind of tunneling in that device. So first of all, you need to see whether people have developed similar devices and which exist in literature. And that should be, basically you'll have to always go with fabricated and reported results. Okay, if there is some that similar kind of a device which is already fabricated, so you select that device, you select its characteristics, and then you set your simulation profile. Okay, but if you do not have that, if you do not have an exactly similar device, then the next question is there any other fabricated device in which the principle of operation of your device is present? It may not be the actual device. Okay, suppose I have a conventional MOSFET. Now I am designing a vertical MOSFET. So in that case, somewhere I can take instance of already fabricated MOSFET. Okay, but I have conventional MOSFET, and now I am going for a FinFET. So this is the first time I am doing a 3D structure. I don't have anything to compare with. So there is no FinFET which has already been fabricated. I am thinking about it for the first time. So in that case, what you are going to do? So in that case, you have to see whether the principle of operation of your device, in FinFET it is also drift diffusion, so it matches with your MOSFETs, right? So then you have to select MOSFET itself. So are you getting my point? Like, if your device, if similar device is already fabricated, you have no issue. You directly pick that up and do it. But if you have a device where you do not find any exact match of similar kind of devices, so you will go to the next level. If you do not get a device, you will go to the next level. You will find a device where something is matching, less matching with your device, but there is a match, at least in terms of the principle of operation. Then you are going to select it. Okay. So, and if still you do not have anything, still you are not able to get a device, then you have to check, is there any report on any model which has validated the principle of operation, however theoretical it may be. So suppose you are trying to do spin transistors, okay, and you do not have data from a fabricated spin transistor. So you will have to then look, you do not have anything in literature related to fabricated spin transistor. So then you will have to see whether someone in terms of physics of that device has developed a model and given enough justifications to make you believe that this is actually the model which is going to be applied in your spin transistor. Okay, so these are some of the basic, you can say, constraints or questions that you must ask before doing a calibration. And if still you do not have, still you do not get anything, you do not have any model, you do not have any device, you do not have any device where a single principle of operation is present, then you go with the default values. Okay, the default values, because your simulator will already have some model which will run on its default values. Always any model will have some default model values plugged into those particular functions. So then you'll have to go with default values once you have answered and got rejections on these three questions. Okay, clear? So these are some of the selection strategies. There are other ways of doing it, but these are the best ones, the best possible scenarios that you can take. So before moving to this, I would like to take up questions if any. I know it has been a very post-lunch session, yawning, and yeah, I do not mind, no problem. Even if I would have been there in your seat, I would have been yawning. Probably I would have been asleep by now. Yeah. Any question, any random question? Because if you ask me question, I'll get motivated to go to the next part. Any question? Anything?
Particular one model.
Yeah.
Will satisfy all the constraints. Is it possible?
No. Very good question. Very good question. Now, in a simulation framework, when we are selecting models, suppose we assume that we have calibrated everything and my device, my simulation setup is ready. Okay, my simulation setup is ready. Now I can analyze my device. Okay, fine. Now the problem here is while calibrating, like before moving into your actual simulation, you must be having something in your mind, right? That like I'm going to analyze this things. I'm going to see this things in my device. Okay. Based on that, actually you have selected your calibration models, which you are actually going to use in your actual device. Okay. Now it has never ever happened that one model is going to satisfy the entire performance of your device. I'm talking about simulation. Okay, in an industrial simulator, whenever we start, we always try to go with maximum number of physics-based models. Okay, but now the problem there is if you are going with maximum number of, you can say, physics-based models and you are simply randomly inserting them, some of them may be conflicting with one another. So that part you have to understand, because as I have said, you have to know your simulator before doing any simulation. So you have to know your models first. Okay, but to answer your question, one model is never going to do that. It cannot describe a device in its entirety. So mobility will have a different model. Okay, then principle of operation, drift diffusion, hydrodynamic will have a different model. Then band gap narrowing will have a different model. If you are having very high doping concentration, then your band gaps will not stay as you have in your silicon. Say for example, if it is 1.1 and you are doping it very highly, then your bands are going to stay, they are going to overlap with each other and you will have an effective band gap, which will be smaller. Okay. So my point is that whenever we start with simulation and whenever we are selecting any device for analyzing it, we'll have to first understand what we are going to do, number one. Second, are the models sufficient that you are going to get by observing literature, okay, or by observing certain characteristics. Sometimes literature is not sufficient, so sometimes you have to go for experimental characteristics and then you have to see and then decide. Third, sometimes you'll have to put models just to check whether it works or not. Sometimes you'll have to put certain models just to see whether it can influence the device behavior or not. Okay, so these are the 3 points, but yes, one model is never going to do the job. Okay, now let us move to the next part, understanding modeling and simulation strategies through different case studies. The first one is the tunnel field effect transistor. MOSFETs is one, tunnel FETs is one. Most of you must be knowing about this, but yeah. So this is the IRDS, International Roadmap for Devices and Systems. Earlier it was known as ITRS. Okay, now it has come, you can say, come under IEEE. So this was published in 2018. Depending on what kind of, you can say, devices you may have in future, okay, or contemporary devices. So basically, if you know, as most of you must be knowing, that IRDS actually gives prediction parameters for different technologies which are existing. So if you go through their documents, these are very good starting points for finding a problem statement in your research for devices. Okay, so IRDS actually will give you the information about what the industry is doing at this point of time. Okay, so they published this in 2018, and after that they did not publish this such kind of diagrams. So in 2018 they gave this scenario where you have these devices: silicon FET, nanopine FET, TFET, then N-germanium, 3,5, graphene FET, carbon nanotubes FET. So these are some devices which they mentioned. And alongside that, in 2013, they also gave a prediction map for up to years up to 2028, like which primary devices are going to stay in research and which are going to go into fabrication. So out of that, this tunnel FET is which we are going to discuss now. Okay. So here you have different kinds of, you can say, devices: nanowire MOSFETs, then 3,5, you can say, FETs, alternate channels. Alternate channels at that point of time was carbon nanotubes and graphene. Okay. Now these are very, you can say, widely explored. And after that, you also have MOS to these 2D materials, tunnel FETs, and non-CMOS technologies. Okay. So out of this, now we are going to see tunnel FETs. Basically, this is the conventional structure of tunnel fill of transistor. Okay, conventional structure means this was the structure which came into existence and which was very widely explored and which was considered to be the best performing device before any other modification came up. Okay, but this does not mean that prior to these there were no structures on defense. Okay, so basically this is now called as the conventional defense. Now everybody says this to be conventional defense. So this works on intermittent tunneling or general tunneling, which also happens in PN junctions, right? In a very high doping and in applied bias, reverse bias, you can have this general tunneling, and it can operate in P and N channel mode, so it is a bipolar device. Okay, but throughout our entire discussion, we will be focusing on only the N channel. Otherwise, it will be confusing. Now here, if you can observe, you have a P plus, you can say source, then intrinsic, you can say channel, and N plus drain. So basically it is a PIN diode, and on top of the intrinsic layer you have put a gate. That's it. Okay, so it is a reverse gated PIN diode, so tunnel diode, and on top of that you have put this gate. Okay, now how does this work? Like why are we going for such kind of structures? Now, if you observe the band diagram on the right, this is the energy band diagram of this device. If you look through the P, I, and cut line. So, if I draw a line here, if I want to observe the band diagram from left to right, so this is how it is going to look like. Okay, it is off state and it's on state. Now, it is off state. Here you can see this black one, this black, you can say, conduction band edge and valence band edge, this black one, you cannot see any kind of appreciable overlap here, okay, between the valence band and the conduction band. Okay, just before going to this, are you comfortable with the concept of tunneling? How many? Concept of tunneling, how many of you are comfortable with? Concept of tunneling, which at least you like know what it does. You are aware, right? Yeah, okay, thank you. So now this band which you see, this does not have any appreciable overlap between the valence band edge and the conduction band edge. Now when I am speaking about valence band edge and conduction band edge, so basically this is your source, this is your channel, and this is your drain. So this is P plus, this is I, and this is N plus. Okay. So here you do not have any kind of overlap. Means had it been like this, then you have an overlap here. Okay. Now in on state, you can create a condition something like this, and this is going to help carriers go from your source to your channel by the action of quantum mechanical tunnel. Okay, so that is the concept of operation of the device. I think you can better understand this from this animation. So you can see earlier when this voltage is very low, gate voltage, I'm talking about the gate voltage. When this voltage is very low, your bands are, you do not have an appreciable tunnel barrier. Tunnel barrier means there has to be overlap between two bands. Okay, like it is just like, for example, yeah, you have kind of like, you have a separable, you can say, disc here, you have water on this side, you have to lift the disc so that it moves this side, right? So it means there has to be some kind of a path. So that path is created by this tunnel barrier. So at very high voltage, you see this particular thing, it constricts. This length becomes very, you can say, small. So basically the tunnel width, it reduces. Okay. So under that action or under that condition, you can have carriers, minority carriers from the P plus source, which can go to the, move to the, you can say, channel by the action of quantum mechanical tunnel. Okay, but whenever we say that carriers have tunneled, actually we are not saying it correctly. Although it has become the, you can say, convention of the, you can say, teaching and the learning process. So because this is not a classical, you can say, concept. So whenever we speak about tunneling, we have to be very careful that we use the word probability, because it is a probabilistic, you can say, situation, right? So basically, whenever we are talking about tunneling, it means that the possibility or the probability of finding the carrier on the other side of the barrier is finite. So that is the actual, you can say, interpretation of tunneling. But as most of us, like, we know about what it is, so we use the words that the carriers are actually tunneled from left to right, from source to channel. But basically, this is the you can say principle of operation of this device, general tunneling, or you can say the band-to-band tunneling. And the main advantage of this principle is that if you observe a MOSFET and if you observe its, you can say, band diagram, so if you take it from source to drain, it will look something like this. Okay, conduction band or valence band. I've drawn only the conduction band edge, but here, any particle here, any electron, this has to cross this barrier to move to the other side. But in this case, this is restricted by these two limits here. Okay, so therefore the thermal footprint of this device is very small. So if the thermal footprint is very small, it means that it is going to have a very good subthreshold swing. Okay, now what is subthreshold swing? It is the manner by which you can reduce 1 decade of, you can say, current for the amount of voltage for which you can reduce 1 decade of current. So basically it tells about the switching performance of your device. Okay, so since this has these limitations on both sides, so therefore its subthreshold swing is very good. And subthreshold swing is a measure of low power applications of field effect transistors. So therefore these devices are now like were mostly explored. Like why it came to be more explored, this is one of the reasons. And if you observe here, the entire operation is dependent only in this region. Okay, if there is a tunneling here, then it means it is going to come down. So that means that I can shrink this gate. I can keep on reducing this gate length up to a portion till it interferes with the primary BTBT region. Okay, so I have, as a designer, I have the facility, or I have the, you can say, ease of reducing the gate length up to a particular critical length where there is BTBT. So this is also another, you can say, advantage of this device, where I can shrink the device and still have better performance. Okay, but now the problem is, now you cannot have something which comes always with advantages, right? Everything has advantages and disadvantages. So what do you think is the disadvantage of this device? What do you think is the disadvantage of this device? So if there is like a constriction in barrier, you are getting your current, right? So we are very happy that we are getting current because of quantum tunneling. But there is one more important question: am I getting sufficient amount of current? Okay, that is the most important question if I am going to use this device in for amplification purposes or for some other driving purposes in circuits, right? And that is one of the disadvantages of tunnel field effect transistors. You generally do not have comparable current as you can say as you go with you can say MOSFETs. Okay, and that is where the research is done to increase the drive current, to increase the on current, so that this can be used in amplifier circuits or drive circuits. Okay, am I able to reach out to you? So another disadvantage, a very interesting disadvantage. A very interesting disadvantage which you can say from the Venn diagram. Let me wind this up. Another disadvantage. Yeah, this is in its equilibrium or in its off state when I am not applying any bias. So if I apply positive bias, then these bands are going to lower, and then you will be having some overlap between here, right? So that is what we want. Another, any disadvantage which you can get from here? Any disadvantage? If I have applied positive bias here, these bands are going to lower. So I can have this overlap here and I can have conduction. Any disadvantage that we can see here? Any other possibility? Any other possibility? Okay. How many junctions? How many junctions does this device have? Two, right? So it means whatever depletion is going to be for these bendings are because of depletions, right? So whatever depletion that you are having, those are the actual points or areas where you are going to have tunneling, right? So if this is one, where is the other one? On this side, okay? But now, just try to see the deductions. Now you have applied positive bias, okay? You have suppressed your bands in the middle. You are having overlap of bands here. You have created a barrier, okay? Do you have a barrier on this side? No, right? Now you try to see, can you have a barrier on this side by changing some conditions of your device? Can you have some kind of barrier, I mean to say tunnel barrier on this side by changing some conditions of your device? Okay, now this barrier is created because of what? Because of positive bias. So this barrier will be created because of negative bias. Because once you put negative bias, these bands are going to lift. So the same condition which is appeared here will appear here, and this condition is going to get transferred here. So basically your bands are going to look like something like this. Okay, so it means you will be having some tunneling barrier here. Okay, now just try to see, this is in negative bias. Now if I plot my current versus voltage for this device, okay, from the information which I have till now, and I know that I'll apply a very simple condition. Whenever I'll be having tunneling barrier, I'll be having current. Okay, that is the condition. So if I have 0 here, you have positive voltage here, negative voltage here. So don't you think your current is going to look something like this? It is going to conduct on both sides, right? Isn't it? Okay. Now, is this a problem? Are you getting it? Yes. Have you understood what I am trying to tell? So, whenever you will be having a barrier, carriers are waiting, right? If they see a barrier, they are going to go because you have already applied an electric field. So, whenever they will see a barrier, there will be some kind of current. So, in positive side also you can have barrier, you can have current. Negative side also you can have barrier, you can have current. So your IV is going to look something like this. Both sides you will have current. Now, do you want this? Do you want this kind of characteristics? Basically, now the question will be in for what applications, but since we are talking about low power applications and primarily digital applications, this is going to fail. Okay? For example, if you want to use this device under CMOS technology, okay, where you have PMOS as the driver, as the load, and then NMOS as the driver, okay, so basically you will be having something like this. Okay, so this is your P type device, this is your N type device, and suppose I want to use this tunnel FETs in this CMOS technology, right? Okay, and here when this is 0 or when this is logic low, still this is going to conduct because you also have this for your negative range. You have appreciable amount of current. So it means there will be a short path from the VDD to the ground because your P type is also conducting, right, in your negative voltage. Assuming that it is plus means by you can say potentials. So in your negative voltage, this is also working, this is also conducting. So basically it will not act as a inverter, CMOS inverter. So it means we do not need this part of my graph. I need this to be like this, flat. So that when my P type is working, my N type should be off. And when my P type is, you can say off, my N type should be working. Okay. So here we have this problem. We see that we have appreciable barriers for positive bias as well as for negative bias because we have two junctions here, and that is the problem. Okay. Now, it's very interesting. Now, can you tell me, are there any mechanisms to reduce that? Now, try to understand. Okay, like for what basic fundamental aspect this is happening? Think in terms of the device design. Okay, for what basic structural, you can say, appearance of the device this is happening? We started with the question how many junctions it has, right? That is the first question. Second question is how are you creating this tunnel barriers? By applying voltage on the gate, right? So it means the culprit is the gate. If there would have been no gate, then your things would have been easier, although current would have been very less. So it means now what we are getting as of now as conclusions is that I want conduction in this part, but I don't want conduction on this part. I want conduction in the positive side. I don't want conduction in the negative side. But now again also I have only one gate which covers both the junctions. Are you getting my point? Where the problem is? So what can we do? What can we do? Okay. Now see, a few minutes back I told that I can shrink this gate until and unless it interferes with the BTBT of this region. Okay. The first point is I need current on the positive side. I don't need current on the negative side. Current is produced by the tunnel barrier. Tunnel barrier is produced by the gate voltage. So basically the gate electrode is the main culprit, and that is where we should be looking. Right? Now, also we know that since tunneling is restricted only in this particular portion, because that is where your bending are, right? So it means I can reduce this gate length up to a very appreciable distance, such that I will stop it just before it enters the BTBT region. Now, because of that, what will happen? Whenever I am applying negative bias on the gate, this gate cannot influence this junction, because there will be a distance between this gate and this particular junction. So basically, this is known as the gate drain underlap. This is known as the gate drain underlap. Okay, and this is one of the very, you can say, widely used techniques to reduce this negative half of current, which is also known as the ambipolar current. Okay, ambipolar current in defense. So this is one of the disadvantages of defense. Okay, and this is how we remove them. I think the explanation is clear. The connections are clear. So this is some history about phylisters. Now, if you observe this device, as I have said, this is an ETE tunnel diode. So basically, you derive its inspiration from a tunnel diode. But Schweitzer in 1952, he had already developed this device and reported. Okay, so this was not known until and unless people started actually looking for tunneling in devices. But this guy, he has already published this in 1952. You can see this snapshot. So in 1952, in Proceedings of the IRE, he had already mentioned this. He never mentioned about the word tunneling, but he had actually built a device where they could build a tunnel field effect transistor based on a PN junction. So this is the actual paper. You can go through this paper. It's a very beautiful paper, and it is written in very lucid language. You can see how he has shifted the different gates and how he has used oil electrolytes in your dielectric, and it's very good to read this particular paper. Okay, so this was the device which he fabricated and he demonstrated this. Yeah, so this is some basics about tunneling which we have already covered. So as you can see, you can have this tunneling here at the junction which is the highest. Okay, the red portion is the highest. BTBT. Therefore, as I have said, you can shrink your gate up to a certain distance, right? Because your main region is here, so you can comfortably shrink your gate. Okay, and this is your expression for tunneling probability, which is the WKB expression. So I think this does not need any mention. Um, okay, anyway, are we going for some break or have I some time? Do we have some time? Okay. So, I will not cover this now because this is mathematics. And I know that just before tea break it is not wise to go with mathematics. Okay. So, I will not go into this. Okay. Now let us discuss this since we are very now a little bit, I think most of us are now comfortable with the explanation of tunnel FETs and how they work. So this is one device which we designed, okay? Like I told in the beginning, we thought of a device that is going to work, then we calibrated it, then we went for the analysis. So this is one of those devices which we thought, okay? So this is basically a tunnel field effect transistor, and its inspiration was drawn from Schweizer's field disturbance. The inspiration was drawn from this device. Okay. Now the reason, there are many reasons, and I think you'll find it interesting why we went for this device. They are very basic, you can say, thought process in this. Now, the PIN structure which we discussed, right, for conventional TFETs, PIN structure. Now we know that these TFETs, they work on general tunneling, which is also available in your normal PN junctions. Okay, try to understand. We have designated the PIN TFET as our conventional TFET. Okay, and these TFETs, they work on general tunneling, which is also present in our normal PN junctions. So the question is, why didn't we go for PN junctions and went for PIN devices? Okay, the answer is that during that time, during that period or era which we are talking about, you could not have technology which could apply like lower voltages in your devices. Your device area was very huge, right? You needed to think about the breakdown voltage of your device. So better than PN junction, PIN, you can say devices had very good breakdown voltages, okay, tunnel diodes. Therefore, PIN tunnel FET became the basis for the conventional TFET instead of PN, you can say TFET. Are you getting my point? Yes, this was due to the technological, you can say, either you can say that the technology was not developed, or you can say that the die areas were very huge. So therefore, they also had to worry about breakdown voltages. So despite the fact that Schweitzer already gave a PN junction based TFET, people actually took up PIN TFET as the basis for your conventional. Okay, because they had to think about breakdown voltage, and an intrinsic layer in between gave a very good breakdown voltage for the device. Okay, but now today, as on date, the scenario is different because now we can work with smaller devices. Okay, we can work with lower voltages. Now we are talking about 0.8 volt drain voltage. Okay, 0.7 volt, 0.3 volt, right? So here our worry about that breakdown voltage is little bit less as compared to that particular time. So that is the reason why we came up with this device. Okay. If you observe, there is no intrinsic region here, and basically you have only two PN junctions. Okay, and it looks like a bipolar junction transistor. Okay, NPN BJT, right? The only difference here are the placement of the gates and the bias. So by altering the bias, by modulating the doping concentration in the design, we can realize this as a tunnel field effect transistor. Okay. Now, the second advantage of this device. Now, when people started with MOSFETs, okay, when people started with this architecture of MOSFETs, okay, they were very happy, okay, because there were no passivation problems. They were able to use this as, you can say, in amplifier circuits. Okay, so the industry was like booming, and they were very happy. We have invented MOSFETs. Okay, but you know, man and his greed, these are very bad things, right? Now today, I need a 48 mega. I am using a 48 megapixel camera, which is not so good. Okay, isn't it? Because I have to capture the supermoon also, isn't it? Now that is where the problem lies, the demand of the industry. Based on that demand, your designs change. Okay. Now people were, if you want more functionality on your die area, it means you will need more drive current. So that using fewer devices you can drive more, you can say, functionalities. Okay. So it means if I come down to one device unit, if it was earlier producing say 2 milliamperes, I will now need 4 milliamperes. Right? So that is how the Moore's law is governed. Demand, I need a megapixel camera. Coming down to how the circuit is rating, it needs say 60 milliamperes. I need to increase it up it to say 120 milliamperes from all the devices, or fewer devices supplying that 60 milliamperes. If fewer devices have to supply that 60 milliamperes, it means one device has to supply more as compared to earlier. Right? Then people came up with, they said that, what happened? Okay. So they said that, okay, now since I have to increase my current, the only way of increasing the current is that I have to increase the number of gates on my device. Okay, because you have more gate, you have more bending, you have more depletion, and then you will have quicker inversion. Okay, so they did this double gate MOSFETs. Okay, this is a very old technology, but people have been doing this and applying this for many, you can say, emerging devices. Okay. Now, the problem with this is, if you are fabricating this device, there are certain issues because you have to put one from the top, one from the bottom. Okay. So there are some kind of, you can say, more number of steps that are required. Okay. Earlier it was simple because you have to put the gate on the same side. So therefore, what we thought that if we have these junctions, and if we put gates on the same side, then we can have this double gate effect by fabricating on the same side of the device. So therefore, the gates are placed on the same side. Okay. So that is another motivation why we have selected this, so that we can place, you can say, more number of gates. Now here you see your source is common to both the drains. Okay. So basically both the junctions are reverse bias, so that you can have the Jenner effect in your device. So if you observe this, if you split it from the middle, this is a very symmetric structure where you have two PN junctions. And PN junctions, if you want to induce reverse bias tunneling, so you'll apply reverse bias between the two, and then you can have the creation of this tunnel. Okay, so this was the second motivation why we went for this structure. Now, this was when we thought that this was going to happen, but we needed to test it, right? So then we calibrated it with existing TFET, and we tried to see its energy band diagram first. So if you observe, there are very good amount of overlaps on both the sides, where you can have appreciable amount of, you can say, tunneling, and therefore you can have current. Okay, so this is one architecture which we did, and currently we are also working on this. We are also looking for fabrication possibilities, and this is fabricable. Although in a bigger diameter, this is fabricable. This is a fabricable device. Okay. Yeah. Let me go back to your ambipolar part, where we discussed about this part that even in your positive and your negative, you can have currents, appreciable current. We do not need the negative current, right? The current is the negative bias. So we introduce this gate drain underlap. There is another way of reducing your ambipolar current. Okay, and sometimes this gate drain underlap this gate drain underlap is used simultaneously with that technique to reduce your ambipolar current in your tunnel filament transistor. Okay. Now, if you observe this band again, so this band, the slope of this band, that you see, this bending that is happening in these junctions, this slope is dependent on the doping concentration on both the sides. Okay. So if you have a PN junction, if you have lower doping concentration, so your bands will spread out. It will become like this. Okay. If you have higher doping concentration, it will become like this. Right? So it means that if I can somehow alter the, you can say, doping concentration here, I can change the slope of this band bending, isn't it? Now my problem is with the drain side of my device, because this is where my ambipolarity is going to occur. So it means I will have to look for changing the doping concentration on the drain. Are you getting my point? Yes? Am I able to reach out to you? So if this is your case, if this is your scenario in very steeper doping concentration, so once you increase the doping concentration in the drain, so then in that case, this is going to spread out like this. Okay, this is going to spread out like this, and then even if you apply appreciable amount of negative bias, the overlap of these bands will be less. So your tunneling barrier creation will be poor in this kind of device. So these two techniques, one is this gate drain underlap, and the other one is the so one is the gate drain underlap and one is the change of doping concentration in the drain. So basically it is known as asymmetric doping method for source and drain interface. That is one technique, and gate drain underlap is the second. Okay, this is how we can reduce ambient polarity in tunnel field effect transistors. Of course, there are other articles which have also explored different methods of doing that, different other methods, but these are the most widely used ones, and these have almost become standards. So when we start with designing a TFET, we usually incorporate this in the first go itself. Okay, the gate drain underlap and asymmetric source drain doping. So let's take a deep breath.